In this video, I will explain how to solve the question 19, part 1 and part 2, specifically part 2 as a matter of fact. So, look what we have. We have these two cylinders in 3D. Here they are. Two cylinders in 3D. We have to describe this curve of intersection. Actually, there are two curves here, clearly visible on this simulation. Each of them, we have to find a description. They look like ellipses or circles, depending on perspective. Most likely these are ellipses, but we need to identify geometrical characteristic of those ellipses. And that's what we're going to do right now analytically. So I will proceed as follows. First, this in 2D, this is like a circle. So for x and y, I will choose very natural choice of parametrization, cos t and sin t. If I take these expressions for x and y, that will parameterize the circumference of this cylinder, xy cylinder. Now, for the z component of my parameterization, for this 3D curve, I'll do this. I'll just solve this for z, and that's my solution. Just solve for z plus minus. I do a sub. I replace x with a cos, and then I use the basic trigonometric identity, and that's the expression for z in terms of t. Right, so this is a part 2, 1 and 2. So if I combine everything together, I see two different parameterizations for each of these two curves. For the first curve, I have this parameterization, cos t, sin t. And for the second one, it's cos, sine, and minus sine. So this concludes part 1, because we have delivered two parameterizations for each of these two visible curves. The harder part is to identify those curves. When I say identify, I mean find the characteristics, geometrical characteristics of those two ellipses. And for that, we need a little bit of geometry. In particular, I'll just focus on this curve. Whatever I do for this curve can be repeated for this one as well. So my first observation will be that for this curve, y equals z. So what I see that my curve sits in the plane y equals z. Or if I look in a section, that will be this bisector. So my curve, these two suspected ellipses, particularly we're now looking at this ellipse where y equals z. If you look from this direction, they will be sitting in this plane. So what I propose to do is to rotate this plane by 45 degrees and see what happens. I propose to rotate this plane by 45 degrees and see what happens. This is how we normally rotate. That's a linear rotation. It's a linear transformation with a matrix which conventionally denoted by r sub angle by which you rotate. Generally, matrix of rotation has the following structure by the angle alpha. In our case, alpha is pi and 4. So in our case, the matrix of rotation has this structure. So all I'm going to do, I'm going to apply this matrix of rotation to my parametrization of the ellipse. Use the application. I'm going to call the new set of coordinates y dash z dash. This first step. It just implements this matrix multiplication. That's what it is. If you substitute for y and for z those formulae from here, this is a resulting 2D vector. So my final parametrization for the curve after rotation, after I rotated this curve by 45 degrees vertically, my y component disappeared because my curve becomes fully vertical. And that's what we have. And here I can recognize canonical parametrization of an ellipse with the radius 1 and root 2. This is the key geometrical characteristics which we have to identify for this curve. So my final answer will be, it's the ellipse which sits in the plane y equals z with the center at the origin and with the radius c, 1 and root 2. This is it. Thank you very much.